Hey, good morning. How's everyone today? Good, good.
Doing well, Nick. How are you doing?
I'm doing really well, thank you. It's Friday too, which is like bonus. And I've been hacking hardware and writing code, so like what could be better? And we are finishing up week 5. We are like exactly at the halfway point of the quarter right now, so half behind, half in front. And people are doing a fantastic job with this course, so I'm really excited for the second half. And we're going to make a big gear change and start talking about trees. So before we get into that, any questions on what we've done so far? All right, well, let's roll back to the beginning, week 1, and let's recap how we got here. We were looking at efficiencies of algorithms, and we began with an unsorted array. My USB is having issues, by the way, so I can't get my webcam to come up, but I got my document cam to go. Let's start with an unsorted array, and let's think about searching. And if you have an array with, n numbers in it, and they're not in any particular order, roughly how many steps do you have to do to search for something in that list? Roughly n steps. So this is what we call order n. All right, if you want to add something to that list, if you want to do an insert, how many steps does that take? Still not worrying about the order. That's good old order 1. Because all you got to do is just store your new thing at the end of the list. Well, where's the end, right? It's a variable that keeps track of how many things are actually in your array. If you've got 10 things, right, just go down to the next one. That's where you store your new piece of data. So insert is really efficient. And how about deletion? So what do we have to do to delete? So it's order n, but it's mainly order n because we have to find the thing we want to delete. So suppose you've already found the item in question. Then how much work do you have to do to delete it from an unsorted array? That's back to order 1. Because here's my array of 12 of a bunch of numbers, and let's say I want to delete the 2. Well, I can just take the 12 and move it up there and say there's my list, right? So to remove a number, we don't have to move things up. We can just take the last item in the array, put that in place of the deleted one, and then subtract 1 from the thing that's keeping track of how long our array is. So that's order 1. So unsorted arrays aren't bad, except search is really terrible. So we play high-low and keep the data in our array in some search order. What does that do to our search time? Do you remember the fancier formula? Log n, good. Log base 2 of n, because when we search a sorted array, we play high-low. We start with the middle element, and if the number we want is bigger than that, we throw away half the array and we just search this smaller array, which is half the size. And we start in the middle of that, and if we haven't found our number, we will throw away half of that list, and now we're working with something a quarter the size of the original. And each step cuts the size of our search in half. So after log n steps, we'll be down to a search of a list that only has one thing in it, and that takes one operation. So this is really nice for search, but then what happened to our insert and delete times? Those went up to log n. Because now if I want to insert something right here, I've got to take all of this and move it down to open up space for the new thing. So that's order n. Order n. Sometimes you can do that with one machine language instruction. If your architecture supports block moves, it's one opcode, one instruction to do that. But that instruction can take a lot of cycles. But like the old Z80 had block move instructions, which were really fun. So yeah, this is log base 2. Although log base 10 and log base 2 differ by a constant factor. It's about 2.3. So this could also be, you know, log base 10 of n divided by some constant, which is the same as log base 10. So really, we don't list the log, and it's kind of because it doesn't really matter, right? Even though the numbers actually work out to be log base 2, same order of efficiency. All right, so we wanted to do something about the slow insert and delete, and so we've been talking about linked lists. And so if we know where we want to do our insert, how long does it take to insert a new node into a linked list? Assuming we're already at the place where we want to insert it. Right, good old one. But what did we do to our search time when we went to a linked list? Back to order n. So these are our choices right now. And we have one approach to doing search that's really good, which is, you know, keep the data sorted. That gets us log n. So we like that. But we'd like to somehow get this order 1 for insert and delete. So this is our goal. And the actual effective time for insert and delete because we do have to find the thing that we want to delete, or we have to find the proper spot to insert. So the actual time for doing those is going to be log n, because it's a combination of the search time and then the actual insert or delete. And so this is what we're heading towards. a data structure that lets us do all the basic operations in log n. And that's pretty good, because log n grows really slowly compared to n. So what's log base 2 of 1,000, roughly? Or alternatively, what power of 2 is approximately equal to 1,000? 1024 is actually 2 to the 10th. And that's kind of convenient, right? Because we like tens. So 2 to the 10 gets you basically to 1,000. How about a million? So that's 20, approximately. How about a billion? Yep. And a trillion, 2 to the 40th. So from 1,000 pieces of data to a trillion pieces of data, that's a 1 billion times increase. We quadruple our processing time. We go from, say, 10 milliseconds to 40 milliseconds. That's really sweet, right? That's a good order of efficiency. You have to get to a ridiculously large number before the log n starts to get to be something that we need to worry about. And this, by the way, is why you feel a little sad when you buy a really large drive and you put it in your system and you look at the available space, right? Because 2 to the 10th is not exactly 1024. And when you buy a gigabyte worth of storage, you're actually buying this much storage. This isn't for memory, this is for hard drives. You're actually getting this much storage, which is not actually 2 to the 30th. It's 2 to the 29 point something. And if you look at the actual number that you have, when your computer reports it in gigabytes, it's in terms of, 2 to the 30ths. But when you look at the box that you're buying it from, it uses this for a value of a gigabyte. And that disconnect gets even more severe when you talk about terabytes. So if you buy a terabyte drive and you put it on your machine, it's something like 970 some gigabytes. It's not actually 1024 gigabytes. It's a marketing thing. So powers of 2, Madison Avenue. All right, so we're working for log n performance on all of these things. So how did we get log n with sorted arrays? 1024 megabytes equals 1 gigabyte. This is correct. But not when you're looking at specs. They'll actually use like 1,000 megabytes for a gigabyte. All right. So here's a sorted array of data. And if we want to search this efficiently using, the fact that it's sorted, what's our algorithm? So we want to find some number n. Divide and conquer. Okay. That's a good class of algorithms. That's what we're going to use here. So what do? We're looking for an n in this list. What's our first comparison that we make? What do we start checking? The midpoint, right? We check this number, 29. And we say, hey, is 29 bigger than or less than or equal to n? And let's suppose that we're searching for the number 42. All right, 29 is smaller than 42. Right away, we can ignore half of our array. And now we have to search this smaller array for a 42. Well, you and I can see it up there, but the computer can't. So what's the algorithm going to do next? What's it going to compare 42 with? Right, we're going to compare right in the middle. Look at the 68. Alright, 68 is bigger than our 42, so I'm going to throw away this stuff and I'm going to work with this sublist. And we're going to start in the middle of that, which is, you know, the only node, 42. Hey, there's the 42, we found it. I didn't know about Tebby bytes. That's kind of cool. Yeah, same as kilobits per second. You find flash drives on Amazon for like, you know, a gigabit flash drive for only $5, but it's a gigabit, not a gigabyte. So, all right. So divide and conquer, right? Each time that we make a check, we throw away half our data. That's where the log n comes from. Now, if we try to do this with a linked list, we get into some problems. So let me put this data in a linked list. All right, standard linked list. So problem with a linked list is we can't do divide and conquer. Anytime that we do anything with a linked list, what do? We start with the first node and we follow the chain of links all the way down the list. What we'd like to do to search this is actually start from the node in the middle. So instead of making our handle to the list right here, let's make our handle right here. Side question in chat, difference between bits and bytes. As far as I know, a byte is always 8 bits. A nibble is always 4 bits. But beyond that, it depends on architecture. So a word could be 2 bytes, could be 4 bytes, could be 8 bytes. So word is architecture dependent, but byte, as far as I know, is always 8 bits. But what is a bit? Could be a qubit. Oh, 7-bit bytes. That's a weird universe. All right. So we start from the middle. So we're going to make our handle, the thing that we use to get a hold of the list, not refer to that first node, but refer to the node in the middle. And so let's still search for the number 42. So we follow the pointer to our list and we see the 29 and we say 29 is too small, right? We know that our number is somewhere in this sublist on the right. And now we have the task of searching this for a 42. Now again, we got lucky this time. If we just search the list from beginning to end, we'd find the 42 right away. But in general, if we just start here and we move down the list, we're at an order n operation. It's n over 2, but it's still order n. So how do we search this linked list efficiently? Where do we have to start? Close to the middle, right? We need to start searching this list right here. Well, how are we going to find that? Instead of having the 29 point to a 42, let's have the 29 point to the middle of the list on the right. So we're changing that next field, and instead of pointing to the next node in the list, we're going to point to the middle node in the right sublist. Okay, well, suppose we were searching for a number smaller than this middle node. Suppose we were searching for 2. We'd need to look in this sublist, and we'd want to begin from the middle of that. So depending on how our number compares to 29, we might want to start from the middle of this list or the middle of that list. So we're going to use a pair of pointers. We're going to have a pointer that points to the middle of this list and a pointer that points to the middle of that one. Now this will look kind of reductionist because I only have 7 nodes, but imagine that, you know, these are really big, this is a really big list, right? Once I found the 68, if that's not the number I'm looking for, I'm going to need to look in a sublist to the left or the right. And same thing, what I'm going to do is introduce a pair of pointers so that from the 68 I can get to the middle of either of those trees. And similarly from the 10, I'm going to get to the middle of the subtree on the right or the left. And since this sublist, you know, only contains one thing, I'm going to make its pointers null. That's going to say, hey, there's nothing else to see here. So I'm going to do the same idea as I had with a linked list, but my node is going to have my data field, but then a pair of pointers. One pointing to the middle of the sublist on the right, one to the middle of the sublist on the left. Got the idea? So now if I want to search for a 42, it's bigger than 29, it's smaller than 68. Oh, there it is. I want to search for 75, it's bigger than 29, it's bigger than 68, it's smaller than 95. 95 doesn't point anywhere, it's not found in the list. So just like a list, but 2 pointers for each node instead of 1. Alright, questions up to here? Hopefully silence means no. Alright, cool. So now we're just going to redraw this in a way that's easier to work with. The way we access this new structure is going to be to start with this node in the middle. So I'm going to put that right here. And I'm going to draw arrows just like this, but I'm going to organize it a little differently. So the 29 is going to point to a 68 on the right, and it's going to point to a 10 on the left. And the 68 is going to point to a 95 on the right and a 42 on the left. And the 10 will point to a 20 on the right and a 5 on the left. This will definitely complicate insertion a little bit. It will complicate deletion quite a bit. But it's still going to be order 1 to do those things once we know where we want to insert or delete from. Alright, so here's a new way of representing that set of 7 numbers. And this is a tree. Alright, so let's talk about characteristics of trees. So first of all, when we draw trees in this class, we're not going to draw the arrows on these lines. We're going to draw trees. The place we put them on paper is going to be significant. And this is a little different from graph theory. So if you've done 215, we did graph theory last quarter. If not, we'll be doing it towards the end of this term. In 215, but graph theory, you know, what was a graph? It was a collection of points with lines between them, right? So there's an example of a graph. And we learn lots of different kinds of graphs and things like that. But one thing we learn about graphs is that, you know, the way that you draw it on paper doesn't change the graph. It's always the same graph. And we have the notion of directed graphs where sometimes we have arrows on these edges, and there could be, you know, multiple connections and so on, right? So we're not really drawing a graph, we're drawing a tree. So we're going to do some things. First thing we're going to do is we're going to skip these arrowheads, and we're just going to draw lines. But the only way we're going to know what points to what is from how this is situated on paper. And so our understanding is whatever is on top is going to point to whatever is below it. So we have these implicit arrowheads. Oh, nice. Vim on a 286. Cool. I'm pretty sure VI ran under CPM. Maybe I'm imagining that. But that was contemporaneous with my VI days, and I think I remember using that. Alright, so a graph is you know, collection of dots with edges. That's basically what a tree is. But a tree is a particular type of graph. So a tree, I'm just going to say nodes and edges. It's basically directed. So a node generally points to another node. So these edges have arrows on them, but we're not really going to draw them. It's certainly connected. So a pure graph could look like this. Right? Technically that's a graph, even though it looks like it's 3 graphs, right? In the purest sense, a graph doesn't have to be connected. We can have completely independent sets of dots. We're not going to do that with trees. Okay? So it's going to be one thing, right? If it's multiple trees, then it's called a forest. So we're going to have our trees being connected. Most importantly, we're not going to allow cycles. So here, for example, I can go from this node to that node and then back to this one. So I can keep repeating myself. I'm not going to allow that in graphs, right? We can go from a 29 to a 10 to a 20, but we can't go from the 20 back up to the 10. And in fact, if I start at any node and I just follow a set of edges, I'll never get back to the node I started with. And that's really important. Okay, so no cycles. What else do we need for a tree? I think that's probably enough. All right, so we're going to mostly work on binary trees. And so a binary tree, we have at most 2 edges coming from any node. For example, I could continue down here and here I've got a one node hanging off of this one. Here I've got 2 nodes hanging off it. Those are still perfectly fine binary trees. But if I had another node here, like, a 13, so I've got 3 nodes coming off of this 10, it's still a tree, but it's not a binary tree. So binary just means 2 or fewer. All right, good so far terminology-wise? All right, so let's go further into the properties of a binary tree. So I'm going to draw a generic binary tree. And let's look at properties of this. Each node has 0, 1, or 2 nodes directly connected below it. This node has 2 nodes coming off of it. This node has 1 node coming off of it. This node has no nodes below it. All right, so we have some terminology. We would say, for example, this node is the parent of these 2 nodes. So parent means that it sits directly above another node. And these 2 nodes we would call children of this node, which is the children's parent. So basic parent-child relationship, right? Parent sits right above these 2 nodes connected below it, and these 2 nodes that are connected below are the children of that parent node. So each node has either 0, 1, or 2 children, which are the nodes right below it. There's also the notion of grandchildren, and so on. So this node is a child of this one, which is a child of that one. So this node technically would be considered a grandchild of that node. And this node up here on top would be a grandparent of this node down below. And that terminology will actually come into play when we talk about balancing trees. AVL trees and stuff. But for now, we're just worried about parent and child. All right, additionally, most nodes have 1 parent. So this node has a parent, it's that one. This node has a parent, it's that one. This node has a parent, which is that one. But there is one node with no parent. Where is that? Right, it's the node up here at the top. So the node with no parent is called the root of the tree. So in this tree, the root is that node right there. And it's the only node that doesn't have a parent above it. And so yeah, this is an upside down tree, right? With a real tree, the root usually would be considered at the bottom, and then the tree spreads out as it grows up. So I don't know, maybe it's an Australian tree, because bottom and top is kind of relative. All right, so we've got a root node, and then we've got children underneath the root, and we've got children underneath those, and so on and so forth. All right, we also have a term for a leaf node, which is a node that has no children. So it's sort of a terminal spot in the tree. And number of children corresponds to the number of edges coming out of a node, right? So at most 2 edges coming out of a node. That's the binary part. If we don't do that, we still have a tree. But binary tree, 2 children at the most. All right, so the most particular type of tree we're interested in this course is a binary search tree. And they're plain old binary trees with an extra characteristic. So here's a binary search tree. And the root is 40. But what do you notice about the way that the numbers are distributed in this tree relative to the number 40? There's definitely more numbers to the right. Do you notice anything about the value of the numbers to the right relative to 40? All the numbers on the right are bigger than 40, and all the numbers to the left are smaller than 40. Well, let's pick another node in the tree. Let's just look at the 50 node. That's not the root of the tree. It's a child of the root. But if we just look at the 50, the same property applies. Everything to the right of that node is bigger than 50. Everything to the left is smaller. If we look at the number 20, now there's the same number of stuff on the left and right, but everything to the right is bigger than 20, everything to the left is smaller than 20. And this is what makes something a binary search tree. So for any node, and when I talk about a node n, I might be talking about the node, I might be talking about the value stored in that node. I'll interchange the usage, right, to keep things simple. So when I talk about a node n, I'm talking about a node with a value of n. So for any node n, all nodes to the right have a value bigger than n, and all nodes to the left are less than n. And I'm kind of assuming here that a number only appears once. If a number could appear in the tree twice, then the numbers to the right might be bigger than or equal to n. But that's a really unusual thing to want to do. So we'll just assume that a number only appears in the tree once. And so we have this nice property. For any node in the tree, everything to the right is bigger than that number, everything to the left is smaller than that number. And if that's a true property, then this is not just a binary tree, but it's a binary search tree. So that's the magic piece. Okay, and why do we care about binary search trees? Because suppose we want to look for something in this tree. Suppose I want to look for the number 47. The only thing we have that gets us to this tree is the root. Right, so that's the root of the tree. So we start with a 40, and we're looking for the number 47. It's not the root, so we haven't found our number yet. But what do we know, given that this is a binary search tree? Where do we have to look now for a 47? Gotta look in the right subtree. There's no reason to look at anything over here because everything here is smaller than 40, right? We're playing high-low. We're back to, CSE224 high-low game. We're looking for something 47. Is this your number? Nope, your number is bigger than that. Okay, I'm going to ignore all of that, and I'm going to search this. Is this your number? Nope, that's too big. Okay, I'm going to ignore all of that, and now I'm just going to search this. Is 42 your number? No, that's too small. I'm going to ignore that and search this. Is 47 your number? Yes. So basically we started here, we went here, we went here, we went here. If you're searching for an 80, we're going to check this and this and this and this and this. If you're searching for a 25, we'll try this and then this and then this. And this is going to be order log n. So we're pruning this tree and throwing away roughly half of the stuff each time that we do a search. All right, more terminology. This whole thing is a tree. This is the right child. Of the root. This is the left child of the root. But that child is itself the root of another tree. It's the root of this entire tree. And so we can call this thing, this is the right child, but we can call this subtree the right subtree. And we could call this thing the left subtree. When you initially build a tree, is the first node you add always the root? Not necessarily. In some cases, yes. In the cases we'll do for a while, yes. But there's times where that won't be the case. Alright, so that's how we search a BST, basically. Start from the root and just keep moving down based on how the root of each subtree compares to what you're searching for. Selling point of a BST over a hash. They're probably simpler to implement. They're still order 1. I mean, they're still order log n. Hashes, why not always use a hash? It takes a lot more manipulation and they're harder to grow, or they take more work to grow. A binary tree we can grow order log n, and it can grow pretty much without bounds. As long as we do what's called rebalancing it, we keep this nice log n behavior. Hash tables can get to be really bad performance-wise, right? If we have a lot of collisions, if we're doing long chains and chaining, that order 1 can go away. And at some point you need to grow your hash, and that can be an expensive operation. And the difference from order 1 to order log n is not always that important to us. All right, let me, you're welcome. Few examples of trees, right? This is sort of a nice example of a tree. This is also a tree, right? It's a node with a structure with a single node. It's got a root, nothing else in it. But that's a perfectly fine tree. This is also a tree. In fact, it could be a binary search tree. I could have something like, 10, 5, 0, -20. That's a binary search tree. Every node has at most 2 children. Every node has a parent except the root. Everything to the left of a node is smaller. Yeah, that's a BST. But it's not a very well-behaving one. If we want to search for a number in here, we're basically just going to keep searching to the left until we find it. This is really a linked list. Performance-wise, it's a linked list. But it's also a binary search tree. All right, here's our last pathological binary search tree. Everybody see it? It's like right there. It's nothing. That is a valid tree. It's basically null. So an empty tree contains no nodes, right? We're not going to use a sentinel like we did in a linked list. So a tree containing one node will have just one node, but an empty tree containing no nodes won't even have, an empty node in some sense. It has no nodes. It is really just null. And that's going to take a little bit of delicacy in implementing our trees in code, but it will work out really nicely. All right, and the reason that we like trees is this whole notion of subtrees, right? We can think of a tree as a pair of subtrees and a root. And if I want to search for something in this tree, and I know that it's somewhere in here, and that this thing itself is a tree, if I've written code to search this tree, I can use that code to search this tree. And if that tells me that my number is somewhere in this tree, I can use that same code to search this tree. So we're going to get into a lot of recursion here. And it's going to make the code really, really beautiful and slick. All right, so we're going to spend the next couple of weeks probably playing with trees, learning how to manipulate them, so on and so forth. So Monday we'll start looking at some algorithms and we'll build up from there. If I see you in 2:15, I'll see you in a half hour. Otherwise, have a great weekend, and I will see you next time. All right, thanks.